Okay, we're going to start chapter 4 in this video here. So 4.1 and 4.2 are pretty related to each other. The main topic that we're going to talk about in these two sections are called exponential functions. Okay, now the main theme in chapter 4 is going to be logarithmic functions, and an exponential plays a role into logarithms. We'll talk about that later once we get there. So the first thing is I want to start with just a basic review of our laws of exponents. So let a, b, m, and n be real numbers with a and b greater than 0. Law 1, it's like eight laws that we should know. Law 1, a to the m times a to the n means I'm going to keep the base and add the powers. So that'd be a to the m plus n. A to the m divided by a to the n means I'm going to keep the base and subtract the powers. So I'd have a to the m minus n. A to the mth power to the nth power, that's the same as a to the m times n power. Okay, a times b to the nth power. So as long as you're only multiplying things or dividing things, you can bring the power into each and every term. That's okay. So I'd have a to the n times b to the n. Or if I had a divided by b to the n, that would be the same as a to the n divided by b to the n. Now, never ever can I bring in the power if I'm adding or subtracting things. I get a wrong answer then. Okay? So it's only if you're multiplying or dividing these inner terms. Okay, law 5, so sometimes work with negative powers. You'll see that coming up here. A to the negative nth power, that would be the same as 1 over a to the nth power if I were to make the power a positive. 1 to any power is always 1. Anything to the 0 power is always 1, not 0. Okay, anything to the 0 power is 1. Law 8, a to the m divided by n power. So I have, fractional exponents. And I can write that using radical notation. So a to the power m divided by n, that's the same thing as the nth root of a to the nth power, which is also going to be the same thing as the nth root of a, whatever that is, to the nth power at the end. Okay, now this alternate formula here, this would be kind of a preferred formula just in general, because depending on the actual numbers for a, m, and n, like if a to the mth power is some really big number that now you have to know the nth root of off the top of your head, that can be a difficult problem. Like, so a is going to be smaller than a to the nth power. So, in general, it's going to be easier to find the nth root of a first, and then whatever number that is, you're going to raise that to the nth power at the end. Okay, so these are our laws of exponents. Now, we should have all been there and done that before with our laws of exponents. Okay, these will come up. You'll see those. So then the section is called exponential functions. If I give you a definition of that term next, it says that an exponential function is a function of the form f of x equals c times a to the x, where a is called the base of the exponential. A has to be some positive number, although it can't be 1, right? Because we know law 6 says 1 to any power is 1. A can't be 1. And c can be any number, just not 0, because 0 times anything is 0, right? If I had f of x equals 0, that would be just a horizontal line right on the x-axis. And I'm not doing anything with horizontal lines here. As a note, the domain of any exponential function is always all real numbers. Okay, so I can let x be anything I want to if I'm plugging in numbers here. So let's take a look at this example here. Suppose that I want us to graph f of x equals 2 to the x and g of x equals 1/2 to the x. Okay, we'll go ahead and sketch these graphs, and I'll mention some things along the way. I'm going to use a table of numbers. Okay, so there's x, there's f of x, and there's g of x. X can be anything. The domain is all real numbers. Okay, so what if I let x be -3? Well, we'll go ahead and graph f first, and then once that's done, we'll use these same numbers here to graph g. So if x is -3, I have 2 to the -3rd power. Well, let's see. So from law of 5, that'd be the same as 1 over 2 cubed. 2 cubed, 2 times 2 times 2, that'd be 8. So 1/8 would be the y value. Okay, so go ahead and plot the point -3, 1/8. That'd be right there. If we let x be -2, next, 2 to the -2nd power, that's the same as 1 over 2 squared, or 1/4. Okay, so there's the point -2, 1/4 on the graph. If x is -1, 2 to the -1st power is the same thing as 1/2. So -1, 1/2 would be on the graph. If x is 0, from law 7, we know that anything to the 0 power is always 1. So this curve is going to cross through the y-axis at 0, 1. By the way, that always happens whenever you're graphing a function y equals a to the x. You'll always pass through the y-axis at 0, 1. Okay? If x is 1, 2 to the 1st power is 2, so 1, 2 would be on the graph. If x is 2, 2 squared is 4. Okay, so there's 2, 4 on the graph. And then if x is 3, 2 cubed, 2 times 2 times 2, that'd be 8. So 3, 8 would be on the graph. And here's what this curve is doing. So we're coming along, we're above the x-axis in quadrant 2, and we're rising slightly. And then we're going to cross through the y-axis at 0, 1. And after we cross through at that spot, we're going to shoot upward and outward into quadrant 1. Okay? Now, x can be anything. Okay? Whatever x is, you'll never have 0 come out of this. You'll also never have a negative. Okay? So because 0 is never going to come out of this, what's going to happen is on the left, I'm going to get closer and closer to y equals 0, but I'm never going to get there. So there would actually be an asymptote on the x-axis there at y equals 0. Okay, and by the way, that's one of the features of an exponential function, is that there will always be an asymptote on the graph. Okay, let's go ahead and graph g of x next. And I'll just use these same 7 values for x like I did with f of x. So if x is -3, 1/2 to the -3rd power, let's see, so using law of 5, that would be the same thing as 1 over 1/2 cubed. 1/2 cubed, 1/2 times 1/2 times 1/2, that'd be 1/8. 1 divided by 1/8 is 8 when I flip the denominator. So the point -3, 8. That point is on the graph. If we let x be -2, 1/2 to the -2nd power, that'd be the same as 1 over 1/2 squared, or 1 over 1/4, which is 4. Okay, so -2, 4 is on the graph. If x is -1, 1/2 to the -1st power, that'd be 2. Okay, so -1, 2 is on the graph. If x is 0, again, anything to the 0 power is always 1. So this curve is going to pass through the y-axis at 0, 1. Again, that always happens whenever you're graphing y equals a to the x. If x is 1, we get 1/2 to the 1st power is 1/2. So 1/1/2, that point would be on the graph there. That's right there. if x is 2, 1/2 squared is 1/4. Okay, so 2 1/4, that'd be on the graph. And if x is 3, 1/2 cubed, 1/2 times 1/2 times 1/2, that'd be 1/8. Or 3 1/8, that'd be on the graph. Okay, so here's what this curve is doing. So we're going to be starting off in quadrant 2. We're going to be curling in towards the y-axis. We'll pass through the y-axis at 0, 1. And then after we pass through at that spot, we're just going to kind of fizzle on out. And we'll get closer and closer to the x-axis. But again, we'll never get there, though. Okay, so there's going to be a horizontal asymptote on the graph of g of x also. It's going to be at y equals 0. Okay. So now any function y equals a to the x is going to look like f of x or g of x. If a is a number that's bigger than 1, it's going to look like f of x. And if a is a number that is less than 1 but still positive, right, because a is to be positive, then it's going to look like g of x. Okay, by the way, the bigger the base, the bigger the shot upward after you cross through the y-axis. So like if I were to graph y equals 5 to the x, I'd have something similar to y equals f of x here, but I'm going to have a bigger shot upward after I cross through the y-axis. Okay? Of course, I can use what I know about transformations to build, infinitely many more functions here. So like what if I were to graph h of x equals negative 2 to the x plus 3? All right, well, let's see. So what are we doing to the basic function y equals 2 to the x? Okay, well, with the negative in front, that means that we're going to be flipping the graph upside down. And then the plus 3 means we're going to have to shift it up 3 units. Okay, so I got 2 transformations happening here to get the graph of h of x. Okay, the graph of f of x, or y equals 2 to the x, I'm going to have to flip that upside down and then shift it up 3 units. So all the points are going to move, right? All right, let's see where some of them are going to land here. So here's 0, 1. When I flip that about the x-axis, that puts me at 0, negative 1. And then when I shift that up 3 units, that puts me at 0, 2. Okay, so the point that was at 0, 1 is now going to be at 0, 2. Here's the point 1, 2. Right? So if I throw a negative in front of the function, that point is going to be at 1, negative 2. And then I need to shift that up 3 units, so that's going to be at 1, 1. Okay, so the point that was at 1, 2 is now going to be at 1, 1. Now all the points are going to move, okay, including the asymptote. That's going to move also. So flipping the graph upside down, that's not going to change, where the asymptote is. But if I shift the graph up 3 units, I'm going to have a horizontal asymptote at y equals 3. Okay, so go ahead and draw that horizontal asymptote, and then we have this curve heading downward and outward into quadrant 4 there. Okay, so something like that. That would be a quick rough sketch of the graph of h of x using what I know about transformations. And, I mentioned this before, but knowing transformations is really important, because like I already know the answer. But before I make any graph, like I know that I'm going to take, y equals 2 to the x, I'm going to flip it upside down, and I'm going to shift it up 3 units. And that'd be huge, for somebody who is stuck point plotting. It's easier to just know what the answer is, okay, rather than making a table and be stuck point plotting there. So again, transformations are pretty important here. Okay. All right. Why don't we go ahead and stop the video right there, and I'll pick up with this example here in the next one.